Welcome to module 2 of database management systems. In this module, we will talk primarily about the introduction to the DBMS. This discussion will span 2 modules, that is the current one module 2 and the next one, that is module 3. Just to quickly recap, in the last module we have discussed about why we need databases, and we have introduced you to different aspects of the course. In view of this, in this module we would familiarize you with basic notions and terminology of a database management system, just at an introductory level. We will try to understand the role of data models and specific languages for database systems, and we would also outline the approach to database design. So, the module outline would be like this, and as we go along you will be able to follow which particular aspect of this outline we are discussing about. So, to start with, we talk about levels of abstraction. A database system, like any other system, is conceptualized in terms of 3 levels of abstraction. At the lowermost level is the what we say is a physical data level or the physical level, which describes how a record is actually stored. So, that is about the physical storage in the system. At the next level, we talk about it. We say it is a logical level, which describes the data stored in databases and its relationship amongst the data. So, you can any data that is stored, you can think about it as a record. So, if we here we are illustrating the record of an instructor who teaches a course. So, as you know, the record is a collection of multiple fields of different types. So, here we have a field to describe the ID, identifying number or string of an instructor. We have the name of the instructor, the name of the department, the salary, and so on. So, this logically says this is the entity, this is the record, or this is the structure of a record that I want at a logical way. So, this in contrast to the physical level, logical level is not concerned particularly with how these data, how this string, the number and all that will be actually stored, and how these multiples of hundreds and thousands of records will actually be stored, so that they can be efficiently used. But we are just concerned with the logical view that I should be able to deal with records as they are. At the third level, which is you can say is the topmost level, is called the view level, where the application program tries to view the data, and when the application program tries to view the data, it deals with the details that it needs to, and rest of the details are usually hidden from this view. For example, if we talked about the university database in the last module. So, if you are talking about the university database, and then you are a student, and when you access the database, you should be able to see what all courses you are enrolled in, where is that course being held, who is the instructor of that course, and so on. But you should not be able to access or see the view of what is the instructor's salary, or for that matter what are the grades that are obtained by different students in different courses, and so on. Whereas, an instructor may be able to view the performance of the students in multiple different courses, particularly the ones that he or she is involved in evaluation, but she again may not be allowed to check the salary of other instructors. So, view level is a high level of abstraction, where you try to provide the information about the data in terms of what the application needs, what the users of that application need, but you do not actually deal with the details of all the records that the logical level has. So, these three levels form the basic structure of a database system, architecture of a database system. As you can see, the physical level, using that a logical level of records are formed. Physical level typically is in terms of database files, is binary in nature, the organization of those files. The logical level deals with the records and the different fields of the records, the schema of the database and so on. And the view level is something which is constructed from the logical level in terms of different views that the different applications need. I am sure at this stage you may not understand the whole of these levels and their implications, but this is just to give you an idea of the existence of three levels and the need to deal with the three levels. And as we go along, you will see that we will refer to these levels more and more and discuss about the specific aspects of those. Next, let us talk about schema and instance. We will very regularly keep on referring about schemas and instance. The schema is in very simple terms, say if we talk about first the logical schema, it is a way a certain data needs to be organized. It is a plan for organizing data. So, if we can draw a parallel, then say when a building is constructed, a plan is prepared, and according to that plan several buildings in a say a residential complex may be constructed. So, there is a difference between the plan which gives you the layout of where different rooms should be, where there is a staircase, where is the courtyard and so on, and the actual building when or the group of buildings which are constructed. So, the schema primarily talks about what is the plan to organize the data. So, if we talk about a customer schema, it has multiple different fields. It should talk about the name of the customer, ID of the customer, its account, possibly the other ID, the mobile number and so on. So, the fact that these fields need to be present for describing a customer forms the customer schema. Whereas, when we talk about a specific schema of account that the customer holds with a bank, then we need the account number, account type, interest rate, minimum balance, the current balance and so on. These are the fields of information that we need, and we need to know what is the type of every such field and all those, and those kind of information form the schema information. And again, in line with the abstractions of physical, logical and view as we did, schema also can be at a logical schema which is corresponding to the logical level of abstraction, and we may also have a physical schema which tells actually how the data is physically organized in the database, what are the different database files, how they are indexed and so on. So, all these information which we can say is kind of a metadata information. This is not actually the data. It is not the customer schema is not saying who the customers are, the account schema is not saying what are the accounts, what is their balance, but it is saying that if a customer needs to be defined, then what is the information that you need to know, what is the information that you need to manage. If an account need to be described, then what are the different fields that are important. So, this schematic or this metadata is called the schema of a database. Now, based on this schema, specific instances of databases happen. Instances when you actually have populated different records according to the schema. Now, naturally once the schema is fixed, your records will need to have values in all of those fields that the schema has, and every value must be of the type that the particular field is specified with. So, I have just shown here certain sample instance of customer schema where you can see 3 customers with their name, customer ID, account number, other ID and mobile number. These are all fictitious data of course, but this is just to give you an idea of how this customer instance would look like. Similarly, we have shown what is a accounts instance. So, you can see that there is a some kind of a relationship that you can see between these instances. For example, the first customer ID on the customer instance can be seen as a first the first account ID in the customer instance can be seen as a first entry, first record in the account instance, and so on. So, when we actually populate the schema with different records, and this is what keeps on changing. So, certainly when we do operations on the database, then certainly very regularly new records will get added, some records might get deleted from this instance, and fields of certain records may keep on changing. For example, in an accounts instance, very regularly whenever a transaction is done, the account balance will get changed. Maybe at a certain time the bank might decide to change the interest rate for a certain type of account, then the interest rate field will get changed. New customers may come into the customer instance, and so on. So, instances keep on regularly being updated, manipulated, added, deleted, updated, but the schema remains unchanged. So, change of the schema is very rare in a database and needs to be done only when the database is designed or when it is being upgraded, because once you change the schema, it changes the way you look at the whole world, you look at the whole database scenario. So, if you are changing the schema at a logical level, then naturally the your view will also get affected, because you are using these schemas to decide how you would like to present a transaction application to the user, or for a balance check application to the user, and so on. But of course, what we would want is between the physical schema and the logical schema, we normally would want certain independence. What it means is the logical schema is what you need to deal with, because it is linked with the view that you have at a higher level of abstraction. On the other end, the logical schema is based on the physical schema. Physical schema is how you are actually organizing the information in terms of the binary files, the database files. Now, certainly you want that logical schema not to change, because if it changes, then at a view level all your applications will have to change. But it is quite possible that your physical schema, the way you have organized in files and so on, might need a change, because maybe it is just that you had designed the database for 10,000 records and you already have 9,000 records, and you would like to expand it to maybe 100,000 records, and the physical disk system needs to be different. You may need to reorganize the files and so on, you may need to index it in a different way and all this, but you would like to do that change in the physical level without requiring any change at a logical schema. So, this property of a database schema is very required, which we say is a physical data independence, or the ability to change the physical schema without actually affecting the logical schema or the view level. So, that will be a critical factor that we will have to keep in mind. So, next is data models. So, data models are a collection of tools that describe the data, because we are talking about a database system. So, certainly the main focus here is to be able to model the data, to be able to represent the data. So, that talks about relationships between data, it talks about the meaning of the data semantics, it talks about data constraints. For example, we say account balance, we just referred to account balance in the account schema and the instance. Now, the question is can the account balance be negative? The answer is yes or no. If the bank mandate that I can only withdraw as much money up to which I have deposited, then account balance cannot be negative. But if the bank is giving me the facility to overdraft, then I may be able to draw more money than I have actually deposited. So, my account balance might look negative. In some banks, it could be that the bank says that, well, there is a minimum balance. So, minimum balance is 5,000. So, which means that my account balance cannot go below 5,000 rupees. The bank will not allow those transactions. So, these are examples of different constraints that might exist in the real world, and therefore, will be required in terms of the data model representation. So, there are several data models that exist today. The most widely used, most popular and most powerful in terms of a certain section of database applications which we are commonly interested in is a relational model, and that is what we focus in this course. So, we will have a major discourse in terms of the relational model, and a lot of things will be developed based on that. But it is not easy to directly design a database in terms of the relational model, because you first need to understand the real world in which the design is happening. So, we normally start with a less formal model known as the entity relationship data model, or ER model, ER diagram, these are commonly called. So, if you recall your knowledge about object oriented systems, and if you happen to know UML, you already know about ER models and corresponding class diagrams that result. So, we will talk briefly about ER model and show you how to do modeling of the real world in terms of the ER diagrams. But then they are not actually models which the database systems directly use, they are subsequently converted to some relational or other model, and which the database systems will use. Next is object based data models. You all would be knowing, familiar with the fact that objects give a better power to represent the system, which objects are not like simple strings or numbers or characters like that. They are a encapsulated concept of an entity which can be manipulated in a certain way. So, like in the real world you have several objects, it would have been nice to have similar objects in the databases. So, quite a few database systems have been designed, used which are object based database systems. So, there are models for those. However, we will do little of that in this course, because it is little bit advanced in notion. The other model which has become very popular is called the semi structured data model. It is primarily in terms of XML. I am sure all of you would be familiar with the basics of XML, which is extensible markup language, in which you can create use tags and use different markups to describe the data. You can say this is the field and this is the value kind of, and this has become a very nice way to represent the data. And XML or this semi structured models are particularly useful today to exchange data between different systems. I may be using a MySQL kind of database system, my friend may be using an Oracle system, and we need to exchange data tables between these two. These two systems will represent the data in physical schema which are may not be compatible. So, we can represent both of them in terms of XML models, convert the data. So, I convert the data into XML, give it to my friend, and my friend can import from that XML into the database. So, XML is a data model which is frequently used in terms of data exchanges. Then there are several other models like the network model, hierarchical model, which used to be very popular in the early days of database systems before relational model came into force. They still exist in terms of the sum of the databases, and some of the newer emerging big data databases actually have started using this old concept in a new way again. So, this is an overall set of data models. So, here I am just showing an example of a relational model data, which is simply looks like a table. So, you can see that on top row in the blue are the names of the different fields which describe the schema. It says that it has an ID, it has a name, it has a department's name, it has salary. They are trying to describe a particular instructor, and then a whole lot of records, rows in that table, which are every row individually is a particular data entry or a record. So, columns are attributes and rows are records that the relational model describe. Some more of that, the instructor table along with the department table. So, the table below describes the details of a department. So, that has its own schema and the individual records. We had of course seen similar instances already in terms of the customer and accounts instance that we have just discussed a couple of while ago. Let me introduce these two terms, DDL and DML. DDL talks about data definition language. So, what the concept wise what we are trying to say is, certainly we have a schema and we have instance. So, we need certain language constructs to be able to define a schema and certain other language constructs to be able to manipulate the data in that schema, or basically manipulate the instances. So, DDL is the language or part of the language which is used to define and manipulate the schema of a database. That is why schema is a way to define a database. So, it is called a data definition language. So, you can define that I am going to have a table called instructor, which will have 4 different fields, each having certain types of data. So, it says that the ID will be a 5-character data. The name would have a variable length, because you cannot say that the name will be of a fixed length, but it will be of variable length. That is what varchar says, but the length will not exceed 20. And similarly, salary will be a numeric data with going up to 8 figures and having a decimal part having 2 parts. So, this way of defining the schema in terms of the different attributes and their types or columns in the table, or trying to define the structure of that table, is the main issue of the data definition language. So, the data definition language compiler generates a set of tables in the data dictionary, where the data dictionary basically contains metadata. As I said, the schema is nothing but a metadata about the database tables. So, which will have the database schema, it will have different integrity constraints. It could say that, well, the account balance cannot be negative, or account balance cannot be less than the minimum balance. So, these are different integrity constraints. It could say that this is the primary key. We will talk in more depth in terms of what is key, and it could also specify the authorization as to who is allowed to access which part of the data and so on. So, these all are part of the schema definition and forms the DDL of the language. In contrast, the data manipulation language is a language for accessing and manipulating the data organized. So, it is for access, update, addition of new records, deletion of existing records and so on. And very commonly we will refer to the data manipulation language as a query language, because this is what you want to know what exists in the database. So, the query language will be designed primarily in one of the 2 ways. One group of languages is known as a pure language. They are more mathematical in nature. They have a formal basis. You can prove that whatever you do in these languages are correct and will give you the correct result. So, there are different languages based on the relational model. They are called relational algebra, tuple relational calculus, domain relational calculus and so on. Of these 3, we will in this course deal only with relational algebra. There are mathematical proofs which show that whatever you can do in relational algebra, you can do it in tuple relational calculus and vice versa. Similarly, whatever you can do in relational algebra, you can do in domain relational calculus and so on. In one sense, that these languages are equally powerful. The same thing can be done in any one of them, but we will just take the simplest of them and study here in terms of the relational algebra. But these are more mathematical representations and not easy to write as a program. So, normally we will use certain commercial query language, which is called SQL for most of our applications, and we will do the coding in that. So, SQL which is the most widely used commercial language, and mind you, this is not a Turing equivalent language, which means that everything that need to be computed cannot be computed in SQL. There are certain computations which SQL cannot do. It is a limitation, it is a restricted language. So, often SQL is used in conjunction with some common high level programming language like C or C++ and so on. So, whatever is can be done in SQL in terms of data manipulation will be done in terms of the relational model, but there could be additional logic that needs to be built in terms of the high level language. So, application programs are typically written through them. So, we can do this through a process of embedding, that is put an SQL as a part of a C program, or use certain libraries which can actually take a query from C and fire it on the SQL database. So, we will see how to do this in the course of time. Coming to the database design aspect, this is a process through which the databases need to be designed, and certainly the first part of the design is the logical design, where you need to identify what are the schemas and what are the constraints that apply, what is authorization required, and first set of decisions about those are related to the business. As we say, business means it basically comes from the domain. So, it's if I am doing an university database, the business decisions will come in terms of I have courses, students, instructors, and the instructor teach courses. Can an instructor teach multiple courses? Can a course be taught by multiple instructors? These kind of business decisions are critical for the database design. And then there is a whole set of computer science decision or the database decisions to decide as to if this is the kind of business information that you want to keep in the database, then what is the kind of relation, what is the kind of schemas that we should use, what should be the attributes, which attribute should be of what type, what should be string, what should be numbers, and so on. So, these form the basis of the physical logical design, and of course, we then need a physical design which decides on the physical layout of the data, what are the different database files, how they should be indexed, and so on. So, here we are showing an example table. So, it has multiple fields. It shows the instructor is just expanded form of the instructor table you saw earlier. It is expanded with the department's name and the building in which it is housed. So, if you look carefully, that this certainly comes from the business decision, that you need to know the department to which an instructor belongs, and certainly you need to know the building in which that department exists. So, knowing the department of the instructor and the building of where the department is are critical, but the question is this a good design? Is this so? We will discuss as to why this is a good. This may not be a good design to represent the data. So, in this module we have taken you through the basic notions and terminology of database management systems, highlighting primarily the levels of abstraction, the schema and instance, the basic data models, the languages that you need, DDL, DML, and the commercial SQL language. And we have also tried to give you a glimpse of the approach that is required in terms of the database design. We will elaborate on these more in the second part of our introduction to DBMS, which will be taken up in module 3.